Cool. So today we're going to be taking a deep dive into this claim about life on Venus.
My original work had said, if you find phosphine on any terrestrial planet, it can only mean life. And that wasn't an outrageous claim until recently.
There's this Goldilocks zone in the atmosphere that is not too hot, not too cold, but just right for life.
And that's exactly where we found phosphine.
He is a co-author on the 2 papers detailing the discovery of phosphine gas in the cloud decks of Venus, as well as determining that the phosphine on Venus cannot be explained by conventional processes.
It's actually a discovery of a biosignature on a planet that has already hints that something really, really mysterious is happening, chemically speaking, on it in the cloud decks of Venus. And we add additional mystery to this list of mysteries that this planet already has.
And the reason that it's interesting is because we know so little about Venus. I mean, with most fields of science, it takes you a long time to read up on everything about the subject. But I mean, if I were to just ask you, what do we know about the surface composition of Venus? You're looking at 2/3 of mankind's entire knowledge of the surface composition of Venus.
As I recall, one of the Venera probes, or maybe several of them, saw particulate matter at a certain level in Venus's atmosphere that happened to be the size of a microbe.
So in an area where you know that things are precipitating out of the atmosphere and are making drops that are getting bigger and bigger, they eventually get comparable to the size of a microbe. You mean like a drop of water in a cloud or something?
And then we have things like dark UV absorbing streaks that seem to change and almost bloom and do all these sorts of things.
You mean like clouds?
All of this seems to converge on the same level in the Venusian atmosphere, though, correct?
Yes. When you get clouds forming, they form micron-sized particulates. I'm not quite sure where you're going with this.
That's correct, and that's a very nice observation. So if we were to be optimistic, then we can say that our phosphine discovery adds another mystery to the layers of mysteries that this planet already has.
Cool, so they're speculating about some sort of floating life making blooms in the sky. And they made some 100 or so pages of calculations about how it couldn't be other naturalistic stuff. None of which is actually terribly impressive because of just how little we know about Venus. In terms of chemistry. I mean, it's rocky, it's very cloudy, there's lots of carbon dioxide in the atmosphere, there's very little water, and it's very hot. Now, let me add some caveats to this. We actually know what the surface looks like in great detail because it was radar mapped by the Magellan probe. And it had to be done by radar because there are too many clouds to actually see the surface in visible light. But even here, where we have a very accurate topological map of Venus, just to give you some idea of how little we know here, the highlands are covered in areas that are radar bright, which means it's sort of semiconductor metal type stuff, but no one knows what it actually is. I mean, it's likely that it's something that's distilled onto the high ground like snow on the mountains on Earth. It's just something that is very reflective in the radar. Now, the atmosphere of Venus, we actually know quite a lot more about, mostly because the Russians dropped some probes into the atmosphere. But when it comes to the surface, we actually know almost nothing about it. That simple question that I asked earlier, what's the chemical composition of the rocks on Venus? Now, if you ask that to most scientists, you'll just get a blank stare because almost nothing is known. All of our knowledge comes from essentially a handful of probes that made 3 X-ray fluorescence measurements from the surface. Cool, that's great. What's X-ray fluorescence, I hear you ask? Well, if you get a material, doesn't matter what it is, rock, say for instance, and you blast it with high energy X-rays, that's just very high energy light, it knocks some of the stable core electrons out, and a very short time later, lower energy electrons fall into those holes and release an X-ray of a characteristic energy for the actual element that the hole was created in. So, boom, you measure the energy of the X-rays that come off, and you've detected that element. Now, such machines on Earth have found all sorts of uses, mostly in mining and metallurgy. And you can pick them up on eBay for about $10,000. And they're awesome little machines. They have compact X-ray sources in them, and they can actually give pretty decent results. So, that's great. We just sent one of those to Venus. We must have great results. Right? Well, not quite. This was done some 40 years ago. The words smartphone and internet hadn't even thought of being invented yet. And these probes were sent by the Soviets. A lot of the actual literature on this is actually, as you might expect, in Russian. Plus, this particular X-ray fluorescence machine had to deal with the conditions of Venus. You know, a few hundred degrees, about the same pressure as you would get under a kilometre of water. And if you want a nice simple way of working that out, an atmosphere of pressure is about 10 metres of water. So if it's 100 atmospheres on Venus, that's equal to about a kilometre of water. Alternatively, it's about 100 bar. That's about the same pressure as in this cylinder here. So, this is now going to be 200 bar, okay? Alright, make sure he's actually braced into the wall. Loud enough? So, whew, quite a blast comes off that. So, in many ways, it's a small miracle that they got a measurement at all. But X-ray sources tend to be fragile and power hungry. So, they came up with a simpler, very robust solution of just using radioactive nuclei as a high-energy X-ray gamma ray type source for knocking the electrons off the material so you can look for the secondary electrons coming off. Now, on the plus side, that's exceptionally robust. It requires no power source, and it's guaranteed to work. The downside is, of course, it's not very intense. So, the measurements that you're going to get, they're going to be a little fuzzy. So, these probes get down to the surface of Venus, they drill a little bit of the surface rock, they draw that sample into the actual probe itself, they blast it with some X-rays, and then they measure the secondary X-ray spectrum coming off the sample, and boom, this is what we know about the surface of Venus. That's it. That's the measurements from the two Venera probes. Now let's just compare that to X-ray fluorescence measurements from later Mars missions. Although I was fascinated to find this out, they still use these radioisotopes as an X-ray source even now. So the main difference between these two is, first of all, they have better detectors on the later machines, and secondly, the Mars missions would typically count overnight to get a spectrum like this, while the entire mission lifetime of a Venus probe was typically about an hour. So we know very little about the surface of Venus. But then again, this is maybe not surprising. I mean, if I gave you two random measurements of rocks on Earth, you really couldn't tell a lot about the geology of the Earth from those two measurements. And the reality is, a lot of what makes the geology on Earth interesting is the reworking that you get from solvents of one sort or another, most notably water. At the simplest level, you get rain and it runs through rocks, it leaches out some of the soluble stuff like salt, and then that dries out and you get things like salt flats, or you can get oceans doing similar things which can leave salt deposits meters thick. Alternatively, you can get hot water that leaches out minerals from rocks and then it cools down later and deposits those minerals. And there's a whole spectrum of ways that this can happen. Now, on Venus, there are likely to be similar transport processes, except, they might be with different solvents like sulfuric acid or something. So what's the mineralogy of Venus like? Well, no one has the slightest clue. We know that Venus is about the same mass as Earth, and if you take a look at the composition of the rocks on the surface, they're mostly oxides. It's oxides of silicon and aluminium, that sort of thing. Very similar to the composition of the Earth. Now, it's likely that Venus at some point in its distant past had water on it. And it's likely that somewhere there's going to be loads of mineral deposits of one sort or another. For certain, we know that the surface of Venus is relatively new. How do we know this? Well, if you get a rock, It just doesn't do anything. It sits there basically in perpetuity. So if you get an impact crater on a moon, say for instance, it's going to be there for the long game. And seeing as the number of impacts that you get from meteors and the such like is a reasonable constant, so assuming no erosion, the more craters you have, the older the surface is. And this is why you can take a look at moons of Jupiter, like, say for instance, Callisto, and say that it's got a very ancient surface. Yet Europa, also around Jupiter, has a very new surface. Now, here on Earth, we have other methods that will erase craters, like subduction or erosion. But on Venus, you really don't get that. The craters that you see on Venus are very well preserved. There's very little sign of erosion on the craters on Venus. So the number of craters essentially gives you a bead on the age of the surface. And that comes out as a fairly new surface of 500 million, a few 100 million years old. And the resurfacing there was from volcanism. Now, volcanism on Venus isn't like that on Earth. With Venus, it looks to be very much an all-or-nothing affair. You see, this is a general problem with big objects, is they can only lose the heat from the surface. So let's take the source of almost all the energy for life on Earth, the sun. It generates loads of heat, yeah? It's a giant ball of plasma sat there in space. It must be generating loads of heat. Yeah, it's generating about 4 times 10 to the 26 watts. But it's also very heavy, with a mass of some 2 times 10 to the 30 kilograms, which means if you take about a kilo of the sun, it's only generating about 1,000th of a watt of power. Now, if that doesn't sound like much, that's because it's not. Your body doesn't just generate a little more energy than that. Your body runs at about 100 watts, and a typical person weighs about 100 kilos. So, give or take, humans are about 1 watt per kilo. Kilo for kilo, that's 1,000 times more than the energy generation from the sun. Now, even if you restrict this to just the core of the sun alone, the energy generation is more that of a compost heap than of a raging nuclear inferno. The reason that it stays hot is because you can only cool down by radiating energy into space. So this is a universal problem, that if you're big, you can only really get rid of heat at the surface. Now, there's all sorts of ways that you can actually heat big bodies like this. You can have tidal heating, as with the moons of the outer planets. And that can lead to the most volcanic body in the solar system, Io, or cryovolcanism on the outer icy moons. But here on Earth, one of the key sources of all the heat being generated within the planet is radioactivity. There's actually quite a lot of radioactive stuff in the Earth. And when that decays, the heat's got nowhere to go. It's got to eventually work its way to the surface to be radiated into space, and that's a very slow process. So what tends to happen is the Earth gets hotter and hotter and hotter inside until something cracks, and the Earth gets a new pimple. This is the main mechanism of getting the heat from the inside to the outside. However, on Earth, this is a fairly continuous and incremental process due to plate tectonics. Now, believe it or not, one of the reasons that this happens is because the surface of the Earth is wet. And when the crust gets subducted, it carries water down with it. Now, I'm not talking like, a swimming pool type levels of wet. We're talking 1% water, barely detectable levels of water. I mean, just to give you a flavor of what I'm talking about here, these are rocks, right? They're actually selenite crystals, which is calcium sulfate with a couple of waters. So sulfates are about 100, calcium's about 40, a couple of waters are about 40. So it's got a molecular weight of about 170, and 40 odd of them are water. So that means this is about 20% by weight water. Meanwhile, rocks that are subducted quite frequently contain a couple of percent water. But it's enough. Once that gets subducted, it lowers the melting point a lot, or the viscosity, depending on how you want to look at it. The water essentially acts as a lubricant. Now, I should stress that by the time you're melting this stuff at 1,000-ish degrees at crazy pressures, a lot of these things don't fall into simple chemical categories anymore. But what is true is when you take the pressure off that system, it goes boom in the most spectacular fashion. You see, when a liquefied gas goes from a liquid or a solid to a gas, it expands typically by a factor of 1,000. So 1% water is plenty enough to blow this molten magma all over the place. The nearest analogy that you can get here is it's like a well-shaken champagne bottle. And when you take the pressure off, it sprays everywhere. Apart from, in this case, that it's molten lava that's being sprayed everywhere. Now, if the lava comes up from deep within the planet, where there typically isn't as much volatile material there, the volcanic eruptions typically look more like they are in Hawaii. It's basically just hot liquid pouring out onto the surface. So what would the Earth look like if it didn't have all of this lubricant on the surface to allow the gradual release of all this nuclear energy from the Earth? Well, it would probably look like Venus. You see, Venus lost its water a long time ago due to the planet's lack of a decent magnetic field, which means that the solar wind can just blow the hydrogen atoms off the planet one atom at a time. You know, it's just one of those things. You don't need as much energy to give a hydrogen atom escape velocity as, say, a big atom like oxygen. So it's a reasonable suggestion that after the planet lost its water, all of a sudden the plates don't slide around as easily as they used to. So you can't release the energy anymore. So the planet just gets hotter and hotter and hotter in the inside until when it finally does break through, it coats half the planet, or more like the entire planet, with lava. Now the reckoning is that the last resurfacing event like this took place about 500 million years ago, and I should stress that a lot of this is pretty speculative stuff. You know, it's more just best guess explanations that match what we know about Venus, that it's got a surface that is relatively new, it looks like it mostly comes from volcanoes, and it resurfaced the entire planet. Now, what Venus was like before this is even more speculative, but it's generally assumed that the chemical composition of Venus is fairly similar to that of Earth, in that it would have had, at some point, a decent coating of water on the surface. Now, the simple truth is, while there are clearly volcanoes on Venus, we don't even know for certain if they're active or not. There have been large spikes of things like sulfur dioxide, which suggest volcanic eruptions, but it's pretty indirect stuff. It's not even certain what kind of volcanoes these are. We simply don't have a decent idea of the magma that is currently building up for the next eruption, whether it contains lots of gases like it would in a subduction zone here on Earth, you know, from when the planet was wet, or whether it's actually just from deep within the planet and contains relatively little dissolved gases. We don't really even know if there's lightning on Venus, which is stunning if you think about it. This is what lightning looks like on Earth, but different space probes have returned different results. Cool, so let's come to the prospect of floating life on Venus. Let's start by defining life as loosely as we can to give us the best chance of a hit here. So I'm going to call life a modestly complex series of self-replicating chemical reactions. On Earth, all life, all of it, falls into the category of cellular life. You basically have a blob with an outside called a cell membrane. And that cell membrane is made up of detergent-type molecules, which they're not that far off oil. So the bare minimum that you're going to need in this self-replicating reaction is it's going to be able to need to produce more cell membrane somehow. Now, on the inside of that cell membrane, you have a bunch of self-replicating chemical reactions. All of this is going on in water. Again, this is all life on Earth. The extremophiles, all of it, falls into the category of basically 70% water and 30% biomolecular crap of one sort or another. Now, that biomolecular crap is made up of 4 basic families. There's the proteins, there's the DNA-type molecules, the sugars, and the oily lipids that make up the cell membrane. Now, you don't have to think about this long or hard to work out that to create a copy of all of these things requires some rather specific chemistry, and you don't have to know that much about chemistry to know that there's only one element that has that spectrum of ability to form chemical compounds, and that's carbon, mostly in compounds with hydrogen, nitrogen, and oxygen. Now, this is the key point that I listed in my last video, is that life is 2/3 water, and water is 2/3 by nuclei hydrogen. And even the biomolecules, which are the rest of the 30% of life, is about 50% hydrogen. But this is the rub. There's basically no hydrogen on Venus. So life here, it's just a complete non-starter. It's like claiming that you can make omelets without eggs. Or in more detail, there isn't enough hydrogen to make proteins on Venus, or lipids, or cell membranes, or base pairs, or sugars. So of all the mechanisms that might be producing phosphine in the atmosphere of Venus, it turns out that life is the easiest one of all to exclude. But for some reason, the authors of the paper didn't do that.
So far, our technique has been proving all the things that it isn't, and we've exhausted everything we've got. With our knowledge of Venus and phosphine and chemistry and geology and planetary dynamics, we cannot make phosphine in any non-biological way.
That's great. And you can't make it biologically either, because none of the molecules that you would need to make life are there. There aren't even the components that you would need to make the molecules of life there. Now think about the requirements of getting all of this into the atmosphere. Remember, if these microbes go anywhere near the ground, it's barbecue time. So if there is going to be life in the atmosphere, it's got to be able to create some membranes. Well, those basically have zero volatility. They decompose before they become volatile, and the same is true of the sugars and the proteins and the DNA. So any organism that is actually floating in the clouds of Venus would have to be able to synthesize all of these on its own just from the raw materials in the air. And they're simply not there.
And also, the third crucial point is missing. There is very little hydrogen available on Venus. And actually, Venus is a planet that is famous, famous because of his hydrogen depletion.
Trying to make any biomolecules similar to those found in the swamp life on Earth that is known to make phosphine, I'll give you a clue. You can't. But these are just circumstantial evidences for why life can't exist in the clouds of Venus.
And phosphine signal was detected on the altitude from around 53 kilometers to around maybe 60 or something like that. Now, this is right within this region of the atmosphere of Venus when these cloud decks are present. And this is right within the region when the temperatures are around 30 degrees, maybe to the 60 degrees in the bottom of this layer, which are actually conductive or conducive to some complex chemistry in principle.
Yeah, with the teensy problem that none of the ingredients for life are there. The nearest analogy that you can get to this is like saying an oven is at the right temperature to cook a cake. Therefore, in principle, there could be a cake in the oven, even though you know that the elements required to create the cake are not there. But you know what would be a real killer experiment here is if, say, for instance, someone had sent a probe to Venus and dropped it through the atmosphere and examined the aerosols within those clouds. I mean, that would certainly show up if there was loads of life there producing this phosphine, right? Now, oddly, the Russians actually did some sampling on Venus like this. So I'm going to summarize the results from their latest probe, which is now some 40 years ago. So what it did is it sucked air through a filter, which caught a load of the aerosols in the air. And the first thing that we're going to take a look at is how much there was in those aerosols. Well, it was on the order of a billionth of a gram per cubic centimeter, or 2 milligrams per cubic meter. Now, I'm sure most of you at this point will be saying, 2 milligrams per cubic meter, obviously. Okay, so I'm going to put that into context of clouds here on Earth. So here we're just looking at the liquid water content of clouds. The actual gaseous water content is actually much higher than any of these numbers. But the liquid water content of clouds, so with the cumulonimbus, those are the rain clouds, you're looking at about 1 to 3 grams. That's about 1,000 milligrams of water. Whereas with the high wispy clouds like cirrus, you're looking at about 30 milligrams. The actual amount of aerosols in the clouds on Venus is about 10 times lower than the wispiest clouds here on Earth. Now, I've got to say, some of these Venus probes, you've really got to tip your hat to them in terms of what they achieved, albeit with a fairly high failure rate. And with some of the results, understandably fuzzy. I mean, the prospect of getting a probe to go through an atmosphere and pull out some 4 milligrams of aerosol, then analyze it with X-ray fluorescence, that's pushing the limit. But it looks like they did that and more, and got some sensible results out of it. Nonetheless, some of their results are really very robust. And one of those is that the clouds are mostly dominated by sulfuric acid, then going into phosphorus oxides. Now that immediately raised an eyebrow for me. I mean, what the hell are phosphorus oxides doing in the atmosphere? You see, here on Earth, if you were to, say, pour out some phosphorus oxides like that onto the surface, they would very quickly react with water to give phosphoric acid, which would then precipitate to give some very insoluble stuff like calcium phosphate, which is a pretty decent rock. And that's one of the key reasons why we just don't have phosphorus oxide on the surface of the Earth. But this is weird. I mean, why isn't this stuff in a more stable form, like, say, for instance, calcium phosphate on the surface of Venus? But once you actually find that it's a known fact that the phosphorus oxides are fairly volatile and make up a large portion of the particulates in the Venus atmosphere, and all of a sudden the riddle of how you get volatile phosphorus compounds like phosphine in the atmosphere becomes a hell of a lot less cryptic. Now, earlier I had proposed lightning making phosphides and the such like, because phosphides produce phosphine when they react with sulfuric acid. But that would probably require phosphate deposits of one sort or another. And if you know that Venus is mostly covered with lava flows, that seems unlikely. Further, you've got to get good lightning for that. And the low lightning, well, you would get that off things like volcanoes, but only if they contain lots of volatiles like water and such like. And that's pretty doubtful on Venus. Now, here on Earth, there are essentially no volatile phosphorus compounds. But once you find out that on Venus, it's the dominant particulates in the atmosphere just below the cloud decks is partially reduced volatile phosphorus oxides, that now immediately becomes the most obvious frontrunner for how you're going to get other volatile phosphorus compounds in the atmosphere of Venus, like, say, for instance, phosphine. And it really doesn't take long to join up the dots. You take this P4O6, which they reckon is the dominant form of the phosphate in the atmosphere, and react that with a little bit of water. You get this phosphorus acid. And what do you know? You get a couple of phosphorus acids together, and you get phosphine. This party is over. Now, in rejecting an obvious mechanism, you have to have some pretty strong evidence. They do actually say they've considered this and that their calculations show that this cannot happen on Venus. Look, they're quite clear that phosphorus acid is not stable to evaporation and only exists in the cloud layer. That's bizarre. I wonder what it decomposes to. It's got to decompose to something. Well, here's Wiki, and Wiki agrees that it's not stable as a gas, that it decomposes. I wonder what it decomposes to. It decomposes to phosphine. But I can see why they might want to reject the obvious answer. Well, again and again, you'll come up against this sort of thing in science. You get an unexpected result, and your options are all science as we know it is wrong, like conservation of energy or something, and you will be heralded as one of the greatest scientists of our time, or you just screwed up the experiment. You know, you put the gauge on upside down, you took the wrong measurement, or you just misunderstood what you were measuring, something incredibly mundane. with maybe the best example of this being Pons and Fleischmann and their announcement that they had discovered cold fusion. Sure, it was incompatible as nuclear science that had been established for decades. Sure, if they had managed to get cold fusion, they would have all died from the high energy particles coming off that cold fusion. But none of that mattered. They went and told the world anyway. This was going to revolutionize mankind. Now, this is an area that might be called pathological science, with maybe the most classical example being polywater, where scientists claimed that they had found a new form of water, and if it got into the oceans, it could turn them all into syrup, killing all life on Earth. Now, in the end, of course, it just turned out that their experimental kit was kind of dirty, and when they repeated it with clean kit, everything was fine. But again, to advance the hypothesis of polywater without shame, you basically had to ignore everything that you knew about atomic physics. Just like to propose the hypothesis of life on Venus, you basically have to ignore everything you know about self-replicating chemical reactions. So this pathological science has some characteristics, like it's difficult to detect or reproduce. Check. Well-accepted theories are overlooked. Check. And loss of objectivity. Check. It would be like taking a single picture like this and saying, well, it could be that there's something in the optical part of the telescope, dirt on the lens or something. But also, it could be, and we shouldn't be ashamed of proposing this, it could be a fleet of alien spacecraft.
This hypothesis of life production of phosphine as a legitimate hypothesis. So we shouldn't be ashamed that we actually put this hypothesis forward.
Which would mean that this is definitive proof that we're not alone in the universe. And then going on for the best part of an hour fantasizing about what this means.
Is, when we finally, if this is life and we confirm it, and then we will be absolutely surprised how absolutely ingenious are the biochemical solutions to the problem of sulfuric acid, that microbial life is actually almost an inevitable consequence of the existence of the universe. And if this is life based on sulfuric acid and instead of water, then it changes more than everything, if I even can say this. But it also proves that the path to the origin of life does not really lead only through water. And that would be a phenomenal discovery.
And so life might not just be next door, it might just be extremely common and inevitable, which means that there's thousands and thousands of possibilities for life in the galactic neighborhood just waiting to be discovered.
So as you can see, it changes everything. It changes literally everything, yes.
Yeah, you can see how, given the mundane explanation of lens is kind of dirty, I know it's kind of obvious and you can sort of see it. But no, it could be an alien space fleet. We should definitely consider it as a hypothesis and maybe, base future missions to Venus about this speculation.
We hope we can send a space mission to Venus, look for complex molecules that would be indicative of life, and maybe somehow even look for life itself.
And if we found it?
Could be game-changing for everyone.
I would be very happy to have a mission that has astrobiology at its core, that actually tries to look for life as its main goal, and maybe even capture it.
Look, I'm all for sending probes to Venus, but not for wasting them looking for life, when the best evidence that you have for life is just wishful thinking, combined with ignoring everything that you know about self-replicating chemical reactions. Now, I've got to say, this is nowhere near as promising as Pons and Fleischmann. I mean, let's be real. If this paper had been honest, it would have been, there's all this phosphorus just below the cloud decks of Venus and a very small concentration of phosphine in the atmosphere, and we're not quite sure how that happens. This wouldn't even make a gamma ray publication. It would just barely be a footnote in the catalogue of things that we don't understand about Venus. But they had to put in, maybe it's floating life. And this could change the way that we understand life.
And if this is life based on sulfuric acid and instead of water, then it changes more than everything, if I even can say this.
And boom, it becomes front page news. I mean, contrary to the author's claims, life isn't some infinitely tenacious process that will always find a way.
We have to be aware that, and I like this quote from Jurassic Park when Dr. Ian Malcolm says that life will find a way. And I'm absolutely sure that, you said life sometimes surprises. I would say that life always surprises.
I mean, the mere fact that the driest places here on Earth, which are 10 times wetter than that of Venus, don't have blooms of phosphine-producing floating bacteria should be ample proof of this. And the conditions here on Earth are much nicer than those on Venus. So if life can't find a way here, where we know there's lots of potential life that could evolve into that niche, what makes you think you're going to get it on Venus, where the conditions are much harsher, where just going near the ground will barbecue any life? So that's the video for today. And remember, Mars is superb at the moment. As of me putting out this video in October 2020, it's stunning, high in the sky at about midnight. And if you get a chance to look at it through a telescope, it's going to be better for about the next month than it's going to be for the next 15 years. Meanwhile, Venus rises somewhat before dawn. So if you enjoyed this video, I'd be grateful if you give it a thumbs up. And if you really enjoyed this video and want to support this channel, you can do it directly through Patreon. And thanks for watching.